So before anything else, let me define what a bordism is. Okay. So suppose we have two closed n-manifolds. Meaning that they are compact and without a boundary. And then a bordism W between them is an n+1 manifold with boundary such that the boundary decomposes into M and N. Boundary of W is strength union. How does it look like in pictures? So suppose that N is 1. So we have closed one manifold, for example, S1. And we have another closed one manifold, for example, two copies of S1. A bordism between them will be a two manifold, such that though these are its boundaries. So something like this. So this is a conference on homotopy theory. So let's start by saying the classical connection between bordisms and the homotopy. So a classical result in differential topology is the classification of manifolds up to bordism. So there is an equivalence relation on n manifolds where we say that M is equivalent to n if exists a bordism between them. And we define omega n to be n manifolds, closed n manifolds up to this equivalence relation. Now, this thing, this is just the set of closed n manifolds up to bordism, but this has more structure, namely, it has the structure, it has an additive structure given by a disjoint union of manifolds, and it also has a multiplicative structure, a graded multiplicative structure. When we look at delta star, so this is a graded ring. Graded ring, where the multiplication is given by multiplication of n. So if you take a manifold dimension n and a manifold dimension k, and you multiply them, you get something of dimension n plus k. So we don't just want to find the equivalence classes of bordisms as sets. We want to describe this graded ring. So classical result goes to thumb is that this graded ring is Z-mod 2 with polynomial generators xn whenever n is not 1 less than a power of 2, where xn is in degree n. So this was solved, and it has also a pretty straightforward characterization. But now one can consider not just closed manifolds, but closed manifolds with some extra structure. So there's a lot of extra structure you can put on it, but we will consider framing. So for M a closed manifold, a framing is roughly a continuous choice of basis for the tangent spaces.
Leor, do you know like xn like what do you know like of a representative?
So there are no representatives. I can't tell you them.
It's just a curiosity. Sorry,
Yeah.
I can Google it later.
Project spaces.
Yeah.
It's like strange.
Real project spaces?
Is a continuous choice of basis. So if we have M, then we want to choose a basis at every point, and we want this to vary continuously. So, so this is an extra structure on a manifold, and we can consider omega n with a framing, which is framed n-manifolds up to framed n-bordisms.
Sorry, do you assume the tangent bundle is trivial?
So this is a trivialization. So framing is a trivialization of the tangent bundle.
Yeah.
So if you have this structure, then you have.
You assume you assume the tangent bundle.
I mean, saying that something is trivial is not like a property; it's data. So you have to get a framing, you have to at least have one such data, but there could be multiple different framings. Yeah, so every frame manifold will have a trivial, but you can have different trivialization, and there will be different elements here. It's like I'm a bit lying, you need like stable framing, but I won't get too much into the details. Okay, so this seems like up to now I've only said stuff about manifolds. Where does homotopy theory come in? So in an amazing result by Tom and also later from Zayagin.
Just to be sure, you divide by the relation of framed n right?
Yes, like the bordisms themselves should have a framing, and the framing should agree on the boundary. Yes, and okay, yeah, and this is also a graded ring, where again the addition is given by disjoint union of manifolds, and the multiplication is given multiplication of manifolds, and you can multiply the framings as well.
But no, the multiplication is not commutative, right? Because the order in which you take the first frame and then second frame actually matters.
The order in which take different framings matter. I don't see why. Don't think it's like okay.
You need to convince us that you can like change the order.
There's comparators up to like same thing with GL that has like an infinity structure by taking the matrices like that. It's another. So that's a general thing. It's a higher
Have commutativity.
Okay, so what it's commutative, we can know exactly what it is because this is the theorem. I mean, not exactly what it is, but at least how it's related to homotopy theory. That this as a graded ring, like with the additive and multiplicative structure, the graded ring of framed cobordisms is isomorphic to the stable homotopy groups of the sphere. So this is a very deep connection, and you can take this and you can develop it a lot further. We also hear more about it in Aria's talk, things in this direction, but I'm going now to jump ahead, do a fast categorification, and consider the infinity n category of points. A basic lesson of category theory is that we don't want just to say when we say that things are the same, we want to remember the data of how they're the same. And here we are taking manifolds and just like taking the equivalence relation by bordisms. So we're forgetting a lot of data. We're forgetting specifically what is the bordism that is relating between the two manifolds. So we want to keep track of this data, and we can keep track of it by looking at the category whose objects are manifolds and whose morphisms are bordisms between the manifolds. And in fact, we can consider a higher version of that where we also consider bordisms between the bordisms. So from now on, all manifolds are framed. So I won't say framed always, but so I define board n, which is an infinity m category. So I'm not going to define it precisely. I'm not going to also define precisely what the infinity n category is, but at least an infinity n category. So it's an infinity category in the sense that it has morphisms. It has objects, it has morphisms between the objects, it has morphisms between morphisms, and so on up to infinity. And the n says that from for morphisms of level higher than n, they are invertible. So I need to give you the non-invertible morphisms up to level n, and then tell you what are the invertible morphisms above them. So what are the objects? So objects are closed zero manifolds, which are just collections of points, finite collections of points. Here. The one morphisms are bordisms between them. Bordisms between them, i.e., one manifolds with boundary. So, for example, this is one more. This is a bordism. This is also a bordism. The two morphisms will be bordisms between bordisms. Which are two manifolds with corners. So for example, if we have those two bordisms, this is the first one, this is the second one, then we have this two bordisms between them.
Don't forget, everything is invertible here?
No. Generally, a manifold will not be invertible. Like a bordism will not be invertible. Like
You have a map.
they almost never are invertible.
Position is not necessarily.
Yeah.
He hasn't gotten to n yet.
Right, yeah.
He hasn't.
Yeah,
what
and
happened to
this is goes up to n, where you get like n manifolds with higher corners. And after that, in n plus one, like in n, we stop having manifolds, and then we just have diffeomorphisms. So they are inverted. So in n plus one, we get diffeomorphisms, and in n plus two, we get homotopies between them, and so on, higher levels. Okay, so we define a category, but here we didn't just have a set, we had a graded ring. So can we lift this structure from the classical context to this higher categorical context?
Equivalent to opposite, I guess.
Hmm?
This category is equivalent to opposite.
Yes. It has quite a lot of symmetries. So extending lifting the additive structure is pretty straightforward. It would still be so the additive structure lifts to a symmetrical monoidal structure. Monoidal structure on board N, which on the objects. On objects, it is the disjoint union. The disjoint union of zero manifolds, and on the morphisms, it will also be disjoint union of manifolds. So, on morphisms, also disjoint union. We just take disjoint union of manifolds. Okay, so this exists. Now, what about the multiplicative structure? So let's think about what we would like this multiplicative structure to be. So we would like a functor from board N times board K into board N plus K. Where here, like the top dimension was N manifolds, here the top dimension was K manifolds, so it would land in things where the top dimensions are N plus K manifolds. So can we construct such a thing? And the answer is no, not as it's stated here. Why not? So there is an inherent problem in the in this product of categories. If I take the category of the arrow, and multiply it by another arrow, I get a square, a commuting square. Which means that I get like such morphisms and a invertible morphism between them. Now, if we had such a functor, which was given by multiplication of manifolds, then we would expect that given a one manifold in board N, which is just a one manifold with a boundary, and we take another one manifold with boundary. Okay, so we multiply them, we indeed get a two manifold with corners. And this is a two morphism in board N plus K, but it is not an invertible two morphism because generally the board will not be invertible. So I know we get a circle, and multiply them, we get a torus. There's no reason that the torus is not invertible. Can compose something with the torus and get something trivial. Time, okay. So the problem really is with this this construction, this product, which gives us a strictly commuting square, where what we really want is something that only lax commutes, where you get a morphism here, which is not necessarily invertible. And this is achieved using what's called the gray product of higher categories. Gray product, which I will denote by X with an arrow above it, which satisfies that if you take the arrow, and you take the gray product with the arrow, you get a lax commuting square. And similarly, if you take further multiplications of the arrow itself, you will get lax commuting cubes, higher cubes. So using this structure, so let's call it a construction. So So this is a part of joint work with Leor Neuhauser and Shai Kedar, which is still a work in progress.
Okay, the thing you drew on the board is the infinity 2 category?
This is an infinity 2 category, yeah.
So it's not representable by any manifold with corners, it's something completely different.
So this is like this construction is a like a abstract construction in infinity n categories. And using it, so let me just say what we're doing. So there is a functor from board n ray product board k into board n plus k, which is given by multiplication of manifolds. Now when we change the source, so now we have a product that gives us a lax tomorphism when we multiply tomorphism. We can define such a functor given by multiplication of manifolds. So this is a lift of the multiplicative structure on the bordism ring. Moreover, recall that we have a symmetric model structure on all of them. This will be bilinear because multiplication commutes with distributes over addition. So in fact, we get something. We get a symmetric monoidal functor from board n. Let's call it the lax tensor product, board k into board n plus k.
What's the difference between the two tensor products?
So this is like the thing that co-represents bilinear functors.
Bilinear in the sense of commuting with colimits?
Commuting with the tensor product. Like this is symmetric monoidal. These are like the additive structure that commutes with the symmetric monoidal structure in both coordinates.
I don't understand, like, if that thing is not invertible, that square with the arrow,
Yes.
it's not invertible.
Yeah, like this arrow is not invertible.
So does it land in the board too, or?
So if you take a one morphism in board 1 and a one morphism in board 2, the multiplication should give you a not necessarily invertible two morphism in board n plus k, which in this case would be really the product of the manifolds. Okay, so this is the story on the side of the manifolds, but as we saw before, the bordisms are not just interesting for for differential topologists, which care about manifolds. They're also interested in, like, they also have a deep connection to homotopy theory. So in case, does this categorified version also has a deeper connection to something like in a higher category theory? And the answer is conjecturally yes. This is known as the Cobordism hypothesis. Let me say a few words about that. Not sure which. We call it the bordism. There is bordism and cobordism, and they're the same thing, so I just call it pre-bordism. So we say in a regular like one category, a symmetric monoidal one category, we say that an object X in C is dualizable if there exists another object which we'll call the dual, and maps which we'll call the evaluation from X dual tensor X to the unit, and the co-evaluation from the unit to X tensor X dual, such that they satisfy the zigzag identities. So if you go from X using the co-evaluation to X tensor X dual tensor X, and then using the evaluation back to X to get the identity, and similarly for the other composition. And for example, in vector spaces over a field K, dualizable is equivalent to finite dimensional. So this is in a one categorical world. What do we have in n categorical or infinity n categorical world? So we see a symmetric monoidal infinity n category. So we say that x in C is n fully dualizable if, so first of all, x is dualizable. And then from the dualizability, we have an evaluation and co-evaluation maps. So we demand that the evaluation and co-evaluation are left adjoints.
Adjoint to one another.
No, just they have a right adjoint, not to one another. And then the fact that they have adjoints, so they have an adjoint and they have a unit in the co-unit, which are two morphisms. And we can ask those two morphisms to also be adjoints if n is at least 3. So the unit and co-unit are adjoints, are left adjoints, which will also be, they will also be right adjoints.
And also even chord, right? Posterior will be also right.
Yeah. And so on until n-1. So for degree n, we can't ask for the n morphisms to be adjoints because we don't have any non-invertible morphisms above them. So if they will be adjoints, they will be invertible and then everything will collapse. But we go until degree n-1. So something which is not too hard to see is that if we take the point, like the zero manifold given by a point in board n, it is n fully dualizable. So I won't say why it's, I won't show the whole structure, but to see why at least it's dualizable, you can consider the point and consider this bordism, which I reminded everything is strings, so this will have a direction, so this would be like a positive point, and this would be like a point with the opposite framing. So this will be the evaluation. And then we will have also a co-evaluation, which will be the thing going in the opposite way. And if we compose them, then we will get something like that, which we can straighten, which is diffeomorphic to just the straight line, which is the identity. So this gives the zigzag identities for the point, and something very similar will give you the higher adjunctions. So the cobordism hypothesis, so hypothesis, which is due to the Dolan, with the sketch of proof by Lurie, is that Borden is the symmetric monoidal category with a fully dualizable object. The n fully dualizable object. Which means that giving a symmetric monoidal map from Borden to an infinity n category C is the same as just giving a fully dualizable object in C. So this is also maybe a very deep connection between like something which is completely geometrical and something which is completely formally categorical. And how does so given that, like assuming if the cobordism hypothesis was true, then it will also characterize the bordism category up to isomorphism. So if you constructed the multiplicative structure on board, there should be a way to relate it to this hypothesis. and this is
Sorry, what was C here? You fixed the N?
C is infinity n chi, symmetric monoidal infinity n category.
Statement is this for any C, for all C.
Yeah.
And fixed.
Yes.
And fixed.
Any C.
Yeah. So this is also with like Shai Kedar and Leor Neuhauser, but it's based on a thing, very similar thing that were proven by similar to things proven by Johnson Freed, and Scheinbauer. Which is that the cobordism hypothesis is equivalent to the statement that the multiplication of manifolds map that we constructed before is an isomorphism. So I think I already introduced, so I can say much more about that, but that's it.